Should every spacecraft have a solar sail? Would a Dyson sphere make the Earth unlivable? And why are planets spheres? All this and more in this week's question show. All right, welcome to the question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops into your brain, just write it down, just like as a comment in any YouTube video, but it's got to be on the YouTube videos. Write them down. I will gather them up and I will answer them here. But also, we do this show live every Monday at 5 p.m. Pacific time. So if you want to watch the show live, ask your questions, see follow-up questions, chat with the community, you should definitely join us 5 p.m. Pacific here on the channel. All right, let's get into the questions. CXE, what about using solar sails to maintain orbit and positioning without fuel? Solar sails are one of the coolest ideas, and I'm really excited about them. And I'm really glad that various organizations are starting to actually test out solar sails. We had a test of a solar sail from the Japanese Space Agency a couple of years ago. We had a test from the Planetary Society with their Light Sail 2, and they actually operated for quite a while in orbit around Earth until finally it was captured by the atmosphere and re-entered. And there was supposed to be a test of a thing called the NEA Scout, and this was going to be a solar sail powered spacecraft that was going to fly to a near-Earth asteroid and visit it purely through the power of a solar sail. And it was one of the CubeSats that was launched on board the Artemis mission. And unfortunately, it failed, and NASA hasn't been able to maintain communication with that satellite, and it looks like the mission is probably lost, and so we won't get a chance to see that. But the underlying idea of the solar sail has been tested enough times that we know it will work. Now it's an engineering question. How big can we make them? How lightweight can we make the material to make these solar sails work? And a solar sail definitely isn't your most powerful form of propulsion, but it is free. That once you deploy the solar sail, then you're just getting the photons coming from the sun and you're able to use that to get around. And what's really interesting about solar sails, like I think when people imagine a solar sail, they imagine some spacecraft that is somehow traveling away from the sun, and then it deploys its solar sail like a sailing ship deploying its sail, and then it heads off away from the sun, picking up speed. And that's not true. That's not realistic on the way a solar sail would actually be used. What would actually happen is that the spacecraft with a solar sail would be orbiting with the Earth at 30 kilometers per second, going around the sun. And then as it deployed the solar sail, it has two directions that useful directions it can deploy the sail. One version is at a 45-degree angle from the sun, so that the sunlight comes up, bounces off the solar sail at a 90-degree angle, and this is causing a thrust onto the solar sail, which causes it to increase the height of its orbit. And so it starts to move farther and farther away from the sun. It's essentially spiraling outward from the sun. And kind of ironically, its orbital speed slows down as it gets farther away from the sun, but it is actually sort of moving away. And so you can imagine a solar sail, say it wanted to go to Mars, it would turn itself this 45 degrees away from the sun, and then it would just spiral outward in these wider and wider spirals until its orbit crossed with Mars. And then it would do the other part of the maneuver. And so instead of it being angled one way 45 degrees, it would angle the other way 45 degrees. And now the light from the sun would hit it and would actually be bouncing off of it 180 degrees from what it was doing before. And now it would be slowing its orbit. And so it would actually start to fall down in its orbit. And if you just kept this going, it would just get closer and closer to the sun. It would just spiral inward to the sun until eventually it was destroyed. And so the cool thing about solar sails, they can be used to go anywhere in the solar system. They can raise orbit and they can lower orbit. It just depends on the angle that you use. And that gives you a lot of ability. So you could deploy a solar sail and attach it to pretty much any spacecraft. And then you could use that as either like a primary propulsion system, like the NEA Scout was going to do, or you can even have it as a secondary or an emergency propulsion system. One idea that was proposed, and I really like this, was that they could attach a solar sail to the lunar gateway. And this would just be attached onto the lunar gateway and just as the gateway was going around the moon, it would be angling itself in whatever orientation was most useful to either stabilize the orbit of the lunar gateway or to change its orbit subtly and to get into a better position. That if you have a lot of time, then a solar sail is the best way to go. And so, like, it's not the case today, but you can imagine a lot of spacecraft that maybe could have been saved if they had a secondary emergency solar sail on board, maybe some small package that flies with every spacecraft just by default. And then they're able to deploy this solar sail and then use it to rescue it into higher orbits or whatever. And so, yeah, I think that solar sails have their place in the various methods of navigation around the solar system. They're slow, but they're free. And there's something really interesting and valuable about that. I'm sure you've noticed the Star Wars planetary name that's appeared above my shoulder, this shoulder. And this is a way for you to vote on the questions and the answers that you saw in this episode. And last week's vote was for Coruscant from Darmo 10 asking if we should change the name Dark Matter to Dark Curvature. And I think a lot of people really enjoyed the answer to that question. So congratulations to Darmo 10. You had the best question. I had the best answer. We make a great team. So once again, when you see the planetary names next to the questions throughout this episode, just write down your vote for the best question of the week, and then we will gather them up and we will celebrate next week. All right, let's continue with the questions. Ben rolls. If we cover the sun in some form of Dyson sphere, wouldn't the array of satellites orbiting render the Earth inhospitable to life? Would not block too much light or reflect too much? So this idea of a Dyson sphere, of course, this is where you figure out a way to collect all of the radiation that is coming from the sun and you put it to some sort of useful purpose. And the idea of a rigid sphere is kind of crazy, and Dyson himself didn't even think that would be the case. But instead, what you're going to have is you're going to have a sphere of satellites that are orbiting around the sun in various altitudes, which together don't let a photon out of away from the sun without it hitting some spacecraft, some solar panel in between. And when you think about it, right, we have already begun the construction of our Dyson sphere. When you think about the spacecraft that are orbiting around the sun that we have already launched with solar panels, they are intercepting some of the photons that would have gone off into space, and they're instead being used to power a spacecraft. And so, I always say, when are we going to start building a Dyson sphere? And the answer is, we have already begun. And we will just have more of these, and we'll have more of these and more of these. And eventually someone will go, let's just make this official. Let's just tear apart Mercury and build the Dyson sphere properly and use all that power. But it will just happen bit by bit, day by day. And in fact, it's crazy. If you just take the gross domestic product of humanity and you just continue it on into the future, it's only a few hundred years before we are using up all of the power that falls on planet Earth, that idea of a type 1 civilization. And it's only like a few thousand years that we are using up all the power that is coming out from the sun. What will we use it for? Who knows? Who cares? You just know that we will just continue to use more energy in the future, and eventually we're going to be harnessing all the power of our star. And of course, we're looking for other stars that have been turned into Dyson spheres. So again, Dyson sphere is not a great name. You probably want Dyson swarm. Now your question is, but would putting up this array of satellites be inhospitable to life on Earth? And yeah, if you had the Dyson sphere closer to the sun than the Earth, then it would block the sunlight from hitting the Earth and the Earth would become inhospitable. In fact, a version of this has been proposed as a way to deal with climate change, that you go and put a fleet of satellites at the Earth-Sun L1 Lagrange point, so the point that's in between the sun and the Earth, and you block some of the sunlight that's falling on the Earth. And that will help decrease the temperature on planet Earth and give us a chance to deal with our carbon dioxide emissions, with all kinds of unintended consequences. So, hopefully people won't sort of take that as the solution. So if you put a sphere of these satellites in between the Earth and the sun, then you would block the light from the Earth would cool down and become inhospitable. on the surface anyway. You know, there probably life would go on at the black smokers at the bottoms of the oceans, but you wouldn't want this. So instead, you put the Dyson sphere farther out from the Earth, on the other side of the Earth. And I think you might be right that there might be a problem with trying to have the Earth and also have a Dyson swarm that is relatively nearby the Earth. You're going to have the heat that is coming off of all of these satellites that is going to be reflected back on the Earth, and it's going to increase the temperatures on planet Earth. And so you're going to need to figure out a way to deal with that, whether you have an opening that planet Earth, where the satellites don't come anywhere near planet Earth, and so we don't get any of that reflected light back on us. So you imagine this like perfect sphere of satellites all the way around the sun, except a 500,000 kilometer gap where the Earth is. And so the satellites are all edge on and they never come close to the Earth. And so you got this perfect sphere except for this one planet that is orbiting around inside it. So I'm sure there's a lot of ways to mitigate the problem. Definitely don't block the light from the Earth and don't reflect all of that sunlight and heat emissions back on the Earth, and you should be all right. Rob Hawk. If you learn that a massive solar coronation is heading straight for Earth, would it help to store sensitive electronic devices in a ferret cage? I don't know what would happen if you put your electronic devices in a cage with a bunch of ferrets. I don't know if like what happens when ferrets experience a coronal mass ejection. But if the coronal mass ejection takes out the electrical grid, would that be a problem for the ferrets? Because they wouldn't have any light and power and heat. Now, I don't know if you're talking about a Faraday cage or whether you're literally talking about a ferret cage, but you know, let's say you do have a Faraday cage and you put your devices into the Faraday cage. That would help. You know, this is like a cage of like, say, copper that will stop electromagnetic radiation from coming in. Yeah, you would probably protect the devices, but you can't put the entire electrical grid of planet Earth into a Faraday cage because we need it. Or a ferret cage. Either one isn't going to work because we need them out there as power lines and as satellites and in buildings and all this kind of stuff. So the big problem with planet Earth and our risk of these coronal mass ejections are the interconnectivity of all of the various devices and power grids that we have. Like if you have 100 houses all on a line, one big circuit, and something causes one of those houses to go out, all 100 go out. You need to put them in parallel so that even if one of the houses goes offline, the rest of the houses stay online. And so our electrical grid, our information communication systems have just not been planned out with that level of redundancy in mind because they're more expensive. It's more expensive to build things in parallel. It's more expensive to build in redundancy. It's more expensive to build in the kinds of hardening that it would take to be able to protect against some kind of coronal mass ejection, solar storm situation. And as I'm sure you're aware, you know, you look at the people in California that had all these wildfires because basic maintenance wasn't done on the various electrical grid in the state. That is how humanity kind of rolls, is we're always running right at the ragged edge of what's possible, of what we need. And not as much time and energy is spent in redundancy and what if and risks. And every now and then existential risks can come along and cause a bad day, no matter how many ferrets you bring to the problem. JH, could you have an irregular-shaped planet the size of the Earth? No, like the Earth is a sphere because of this term called hydrostatic equilibrium, that the total amount of gravity of the mass that makes up the Earth overcomes the tensile strength, the compressibility of these materials that make up the Earth, the metal, the rock, etc. And so it's able to smush the planet through its gravity into a sphere. And you could have much smaller objects than the Earth still turn themselves into spheres, even though they're made of mostly the same stuff. When you look at Mercury is dramatically smaller than the Earth, and it pulls itself into a sphere. The moon is even smaller than Mercury, and it pulls itself into a sphere. And so you get down to objects that are just a few hundred kilometers across. When you think about, say, asteroid Ceres or Vesta, they are still smaller than the moon, and they still pull themselves into a sphere. Now, there are some irregular objects that are even smaller, but now you're in the just couple hundred kilometer range before essentially the compressibility of the material, the rock and the metal that makes it up, is stronger than the force of the gravity that's attempting to pull it into a sphere. But even so, it's sort of a blob. It does the best that it can. And so when you think about like planet Earth, the size of the mountains, Mount Everest at like 8,000 meters tall, that is about the largest possible mountain you can have on the Earth. Beyond that, the force of gravity is just continually trying to flatten out these mountains and add them to the curvature of planet Earth. And so you're always dealing with hydrostatic equilibrium. And so I was wondering, could there be some kind of material, and I don't know the answer to this question, but could there be some kind of material that can overcome the compressibility, overcome the gravity? Like if you had a planet made of diamond, would the planet be able to overcome, how big could a planet made of diamond be irregular? And I don't know the answer to the question. So, that's possibly beyond my pay grade to perform those calculations. But that's why everything looks like a sphere. If you like my answers to your questions, as well as the other things we do at Universe Today, consider joining our Patreon club. This allows you to keep minimum ads for everybody. As you can see, there are no ads during the middle of this video. As a patron, you also get an ad-free experience on universetoday.com for life. Even if you unsubscribe, you get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. If you've been sitting on the fence and you've been thinking about joining our Patreon club, you're like, oh, I really should get around to it. I really like what Fraser's doing. Having a trusted, dependable space news source is important to me. Now's the time. Just go to patreon.com/universetoday to sign up. It's painless, I promise. And if you don't like it, you can just quit. And now you've got no ads for life. So definitely join our Patreon group. All right, and thanks to everyone who's already subscribed, and welcome to the recent newcomers like Cherry, Mutaz Hawk, M. Herder, Susan Batchelor, Corporal's Macro Guy, Robert Harley, Joel, Stephen Lawson, son of Sofaman, Marilyn McGee Powell. Join the club at patreon.com/universetoday. Church discography. With current tech, what is the smallest rocket size that could take a tiny payload to orbit? Do you think it could ever reach a hobbyist level? So the smallest rocket that has ever launched into orbit is a Japanese rocket of the S series. And so one of them was the SS-520. And this rocket was able to launch and make an orbital launch. It's about a 9.7 meter tall rocket. So, about the height of a house. It had a total mass of about 2,600 kilograms, and it was able to reach an apogee of 1,000 kilometers. And it was able to launch a teeny tiny CubeSat into orbit. And so that is the very limits, really, of the smallest rocket that humanity has ever built. And that was just a couple of years ago. And so I guess the question is a rocket that small within the capability of hobbyists, amateurs? Maybe, just barely. I mean, if you took a bunch of knowledgeable rocket engineers and you set them with the task of building a tiny rocket like that, then they probably could. It's pretty small. So, but I don't, there aren't a lot of uses when you think about a small rocket like that, all of the time and energy and effort that goes in to build a rocket that all it can launch is a tiny little CubeSat into orbit. It makes a lot more sense to go with a larger rocket and add your payload to a much larger launch and just pay a company that uses reusable rockets like SpaceX. But still, yeah, I would say it is theoretically possible. You had a motivated group of people who knew what they were doing and they're willing to spend a few $1 million, they could probably build an orbital rocket. Zeus Gaming, can we detect artificial light on Proxima b? So you're talking about Proxima Centauri, which is of course the closest star to the sun. and it is a red dwarf star that is loosely affiliated with Alpha Centauri, the twin sun-like stars that orbit around each other. And we know that there is at least one planet, at least 2 planets around Proxima Centauri, maybe even more. And I think one of them is in the habitable zone of the star, which would be really exciting. Now, could we be able to view it? Now, the good news is that because Proxima Centauri is a red dwarf star, the difficulty of blocking the light from the star is dramatically less. Like if you were going to try and image an Earth-sized planet orbiting around a sun-like star directly, then you're looking at a factor, you have to block the light from the star, and the star is like a billion times brighter than the planet itself. So that's like a lot of change in brightness, and we don't have a lot of good ways. You got coronagraphs, you got these ideas of sunshades, but it's tricky. But when you've got the light from a red dwarf star to the light of its planet, then it's a lot more reasonable. Say you're only looking at a factor in the tens of thousands, I think. And so a coronagraph like the one that's on board JWST might be able to do that. But there's another really monster telescope that's in the works here on Earth called the European Extremely Large Telescope. And this is a 39-meter telescope, again, equipped with a coronagraph, equipped with interferometer, equipped with adaptive optics. Like it will have the ability to image potentially planets around Proxima Centauri. But you're specifically asking, could we detect artificial light? Could we detect the cities? And like my guess is going to be no. When you think about like, yeah, when you're in orbit around the Earth, you can see the city lights. It's very obvious that there is humanity here on planet Earth. But when you think about the overall brightness of planet Earth from some distant observer who can only see 1 pixel of planet Earth, would they be able to know that there's city lights? Now you might be able to work it out. Because when you think about it, if you just go through the thought experiment of what it would take, like you've got the planet, you've got oceans, and you've got land, and as the planet is turning, you're going to get changes in brightness and reflectivity depending what the light is hitting us, because it's bouncing off the land, whether it's bouncing off the clouds or whether it's bouncing off the oceans. But then the cities are going to be on the land, and they're going to be changing the brightness of the land parts, but they're going to be doing it only when you're seeing it in the nighttime. And so if you did long enough observations of Proxima Centauri b, like, and I don't know what the amount would be months, years, decades of observations, you might be able to tease out in the data the existence of city lights. Or you just go to a bigger telescope, or you go to the Solar Gravitational Lens Telescope, and then you get a 1 megapixel image of the planet around Proxima Centauri. Yes, please. I think that's what I want. Tim871965. Hey Fraser, how old was the universe when the first ice was able to form? So to get ice, you're going to need water, and you're going to need to have the temperature be colder than the freezing temperature of water ice, 0 degrees Celsius. I don't know, what is it? 32 degrees Fahrenheit. So you would need to have the universe. You need those 2 things. You would need to have the presence of heavier elements like oxygen that could form with hydrogen and make water, and you would need the temperature to be low enough. So Avi Loeb, the guy behind Breakthrough Starshot and other things, he wrote a paper a couple of years ago called The Habitable Epoch of the Early Universe. And he made the calculation that if you just look at the cosmic microwave background radiation, like when it first formed, when the universe had cooled down to the point that the cosmic microwave background radiation was able to escape into the universe, then the temperature was about 3,500 Kelvin. It was about the temperature of a red giant star. Earlier than that, everything was ionized, and so the light couldn't get out. But then as the universe cooled down, the entire universe just got cooler and cooler and cooler. And according to Loeb, the temperature reached the habitable zone of between 10 and 17 million years ago. Another million years after the universe began. So in other words, at about 10 million years after the universe began, the entire universe was 100 Celsius, like boiling water. And then at 17 million years after the Big Bang, the entire universe was 0 degrees Celsius. And so, according to Loeb, 17 million years, that if there was oxygen present in the universe, which there probably was some at that point, then you would have had ice started to form randomly across the universe, wherever hydrogen and oxygen could come together and start to form into ice. And it's such a neat idea, like that for 7 million years, the entire universe was in the habitable zone. But you didn't have heavier elements. You didn't have a lot of rock. You didn't have a lot of metal. You didn't have a lot of water. You didn't have all that other stuff. That all had to wait for billions of years for stars to go through multiple cycles until you got those heavier elements. But if there was some amount somewhere, there was an entire universe for it to form inside of. And that's where the habitable zone was. So at the very earliest, it would be 17 million years after the Big Bang. All right, those are all the questions that we had this week. Thank you, everyone who asked the questions in the YouTube comments, and also everyone who showed up for the live show. Always a lot of fun. Remember, we do this show every Monday at 5 p.m. Pacific time here on the YouTube channel. And don't forget to vote for the question that you thought was the best. The planet names were right there above my shoulder the entire time. And now provide the vote. And ask a question, but also provide the vote. If you want to stay on top of all of the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Tim Whalen, Dave Verabioff, Joff Schultz, and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.